Thank you everyone for coming. This is the second crossing seminar by Camillo De Lellis, who is a professor at IAS and undoubtedly a great mathematician. He also has a Wikipedia page, so you can find all the information you want on Wikipedia. Today he's going to talk about when reason produces monsters while it is wide awake. Thank you very much. You have the floor.
Thank you. It's going, right? Okay. Excellent. Well, it's a great pleasure to be here. So this is my fourth lecture this week. It has been a fantastic, enjoyable week. And I hope you're going to enjoy this lecture as well. OK, so let me start with, so I'm going to actually tell you 3 stories. So this is the first tale that I'm going to tell you. So this person over here is André Marie Ampère. And I mean, we should all be actually familiar with him because, you know, his name actually appears all over the places, and particularly on batteries, right? I mean, it's the guy of the amperaggio, as we say in Italian, of the batteries. OK, so back in the day, he actually claimed the following. I'm going to give you kind of a formal statement of the theorem that he claimed, but the theorem, like in layman terms, actually says that you have a continuous curve. It might have a few jagged bits, so a few bits in which, like, you know, you're not kind of smooth and nice, but overall, there would be a lot of sections which are kind of smooth, okay? So this is just a layman way of stating the following theorem, that every continuous function f from the interval into the real is actually differentiable at some point. So he claimed this theorem, and he actually published a proof, which by the middle of the 19th century, almost every textbook actually quotes. And according to what you actually can find online or, like, you know, in stories, Gauss actually believed this was correct. So his proof actually is remarkably interesting. So he says that there are 2 things. So first of all, on some interval, a continuous function must be monotone, which kind of looks like, you know, plausible. And then out of this, you actually say that a monotone function is differentiable at many points. And it doesn't have actually a proof of neither the first nor the second, according to our standards. But the second statement is correct. And it's, in fact, a famous theorem in real analysis. At any rate, the theorem is actually wrong. It's famously wrong. So it's just simply not correct. And the first one to claim a counterexample is actually Bernard Riemann. And he tells this to his students, that he believes that Ampere's proof, that Ampere's actually theorem is incorrect. And he thinks actually he has a counterexample. So it is not recorded, like, you know, written somewhere what Riemann's counterexample is, but there's a story of what it was supposed to be. And in fact, it's not a counterexample. It has a few scattered points where the function is differentiable, which is not that easy to prove. But truly, Karl Weierstrass actually, in 1872, he announces publicly that he has a counterexample. And its announcement on a meeting of the Royal Society of Prussia, of the Scientific Royal Society of Prussia. I will spare you actually the German name. He announces this, and actually he doesn't publish a proof. It's published way later, because this is just a conference. But Dubois-Reymond actually writes to him because he's very interested in this fact, and essentially in a letter writes to him asking if, you know, please, Karl, give me the argument, because, you know, I'm very interested in it, and I couldn't come to the conference. And this is what actually is published in 1874, of course, with the permission of Weierstrass. Now, in 1920, Czech mathematicians actually discovered a manuscript by Bernard Bolzano with a different example of this, which is way earlier than Weierstrass. The Bernard Bolzano is actually a very interesting character. He's a Bohemian Catholic priest, but of Italian origin, actually. So his father was Italian, and he was appointed to the chair of philosophy of religion in Prague in 1805. So it wasn't mathematics, actually. He's, you know, the reason for being appointed at the university. It was more religious and, in general, philosophy. But now this guy had a strange idea, or, like, you know, the maybe wrong idea of telling the authorities that, you know, kind of religion wouldn't really sanction something like having an army or waging wars. And the Austrians well, the authorities of the Austrian Empire weren't that happy with this. And essentially, they told him, like, okay, look, man, no, this is not okay. Professor at our university cannot say this. So, they were nice anyway. He wasn't sent into a gulag. But one thing that they did to him is that he couldn't publish his ideas in kind of mainstream journals. Not even math ideas. He actually apparently turned to mathematics, maybe because he, it might have left a sour taste, actually, what happened. And so he actually started publishing his mathematical papers, but in kind of more obscure journals. And this is one of the reasons probably why we don't know that actually he had an example. So this is actually a simulation of the Weierstrass function. I will tell you at a certain point how this is done. So this is taken from the internet, but it's very easy to actually write down a program and get an idea of what this Weierstrass function does. And if you actually examine what is really going wrong is that it doesn't seem that this function is really like increasing or decreasing anywhere. I mean, everywhere you are actually, it's always kind of oscillating. It's always kind of having like, back and forth. Okay, so now this is 3 comments which were made by contemporary, very famous mathematicians. So the first one is from Émile Picard. If Newton and Leibniz thought it possible, the differential calculus would never have been invented. So the guy obviously didn't like this example. An outrage against common sense. They are invented on purpose to show our ancestors' reasoning is at fault, and we shall never get anything more out of them. So I actually gave it red, right? So Henri Poincaré. I turn with terror and horror from this lamentable scourge, Charles Hermite. These are either my translations from the French or like, what I found actually online. I guess, all of you guys must have noticed what these 3 mathematicians have in common, right? Is there anybody who can make a guess? Like, yeah, right, okay, fine. Should I say it? So they're all 3 French, but one should actually be fair to Frenchmen, like, because Dubois-Reymond, instead, he was very interested, and he's French, and like, he wrote to Weierstrass, and he was the one who published the proof. So, it's always fun to make, it's always good to make fun of our cousins, as we call them in Italy. Anyway, so, in spite of the forecast of Poincaré, like, in 1827, the botanist Robert Brown, so way earlier actually, discovers that particles of pollen in water move chaotically, and nowadays the way you describe this is the Brownian motion, which is a random walk, and incidentally, a random walk is continuous nowhere differentiable function. So, like, okay, this stuff didn't have any application, or like, would never have any application, but actually for us, it's kind of a common object. And also, like, I don't know, if you follow, for instance, the stock market, you're not seeing something differentiable in the oscillations of the prices, right? I mean, you just see something like that, at least to a fairly good approximation. So this is like a random walk, a simulation that you can find on the internet, and except for the fact that there's some randomness, so you don't see such a nice structure as you saw on the Weierstrass function, right? I mean, which you saw a lot of periodicities, and this was not by chance, but you see something which is very similar. Okay, so now let me tell you actually a second tale. So this, there's some young people over here that will not really understand what I'm talking about, but most of you, I think, are old enough to understand this. So say you're driving a car and you're lost in the middle of some forest, so that you cannot actually get access to the GPS, and your mobile phone maybe is dead, I don't know, something like that. So of course, how do you actually get your way around? You need an atlas. So for some of you, this is kind of a common object. I mean, you've seen it when you were younger, but for the youngest people, this was a collection, a road atlas was like, books like this in which you had a collection of maps which were kind of, giving you the places where the roads are actually put. I mean, like something like Google Maps, but on paper, because you couldn't simply just, log in somewhere. And of course, like, Google Maps, you can just, browse on your mobile phone and like, move where you are, but there you have paper, so what people did, they printed like, many pages in which you had many different areas, okay? So what is an atlas? So an atlas is a collection of charts, right? I mean, like you just have all these pieces of papers in which there are some charts which are printed on it. Each chart actually marks the roads for you, so that like, if you want to go, I don't know, to Ascoli Piceno and you're coming from Ancona towards San Benedetto, then you have to turn right at a certain point. Actually, it also has some curiosity. It tells you their length, the old atlas. I mean, they tell you, for instance, from here to here, there's a little number, which is 9. It tells you that's 9 kilometers, essentially. So, of course, these charts, actually, they have to overlap a little bit, right? I mean, because if you happen actually to be at the boundary, it's going to be difficult for you to understand where you have to go. So they're not exactly precise. They have a little overlap. So there are some places which are actually accounted on two of the charts, right? So, of course, you have a way to compare overlapping portions of the charts. So this looks very much like what in mathematics we call an abstract Riemannian manifold. So this you have to think about a mathematician atlas. So you have a bit more precise description. So there's something called topology, differentiable atlas, coordinate charts. But by and large, it's like I told you, maps don't have to be two-dimensional because, the word of the mathematician could be like of dimension 723. Whatever that means. It's not going to be interesting, actually, for our conversation anyway. And locally, you have a much better description than just some numbers which are telling you the kilometers of some roads. You actually have a precise way, which is called the Riemannian metric, which actually allows you to measure the length of everything which is on your chart, in principle. So it's a lot of information. So, of course, geographical maps are a distorted picture of the real landscape, right? So maps are flat, but the landscape in which we actually live is corrugated. I mean, you have mountains, you have valleys. So it's not an exactly precise depiction in the sense that you take reality, you zoom it back with a scaling factor, and that's what you find on the map, right? In fact, Earth is curved, right? And if you look at a usual atlas, which is kind of a projected thing, right, on a piece of paper as well. In a global chart, typically the poles are very stretched, right? I mean, because they would be kind of, points, but on the global chart, you actually see them this big. So Greenland looks huge, for instance, compared to Brazil, right? I mean, you see over here Greenland, and it looks kind of as big as Brazil. I mean, maybe you could argue whether it is really as big as Brazil, but bigger than Brazil, but certainly approximately so, right? But you're in for a big surprise, right? I mean, Greenland actually has a surface area which is approximately 2 million kilometers square, and Brazil has a surface area which is like around 8 million kilometers squares, right? So actually, Brazil is 4 times as big as it. This is recorded, right? OK, so I live in the US, and I didn't have a citizenship. So with this guy, apparently, you're wondering whether you could actually make this joke. But I'm not sure everybody told him that actually Greenland is not that big, and maybe this is the reason why he wants Greenland. So, but OK, so let me go back. Yes?
I saw an article in the news that saying that Trump wanted to get Greenland
because it looks big. See, so like, OK. Now, this looks like engineered, but actually, bits and pieces of these lectures have been given somewhere else. And this idea of Greenland and Brazil is as old as 8 years. So it was not that long. But this morning, I was kind of reviewing and saying, OK, this is fantastic. Well, anyway, so the lengths written on the atlas, on the other hand, actually correspond to the real ones, right? And normal roads atlas depict actually real portions of the Earth. So here's a question that you could ask, right? So every hypothetical Earth would have a road atlas, right? But, it might be a funny question to ask, but for a mathematician, it's a very interesting question. So if I give you an atlas, which I dreamed of, can I actually realize it with an Earth? Why would you ask such a question? But these are the type of questions that mathematicians actually like a lot. I mean, there's some reasons anyway. There's some very deep reasons. So in precise mathematical terms, I'm going to give you some formulas. So if you are on a Riemannian manifold, so this is sigma, think about it as the two-dimensional plane. And then you have this quantity G, which is a way to measure curves. It's a scalar product. So you have a precise formula for the length of any curve gamma. So gamma is a map from an interval which is going into your sigma. So you compute the length of the, you compute kind of the instantaneous square of the speed if you think that gamma is the way you're actually going through your path, right? Through the Riemannian metric, and then you take the square root, and you integrate in time. And that gives you the length. In the Euclidean space, the length is just the integral of the absolute, of the norm of the derivative of your path, which is just summing the square of the derivatives of all the components, right? And this is the formula that you have over here. And what you're asking is if there is a length-preserving isometry between some word sigma, right, which is sort of, in this case, like a two-dimensional chart, or like, two-dimensional piece of paper, if you want, and some Euclidean space, which, is going to be the three-dimensional space, r to the power 3 for us. I mean, here I can put any n. And the fact that actually the length in your chart is the same as the length in your kind of, real three-dimensional space is given by the property that when I measure the length in the chart in this way, so when I take this formula, is the same as if I measure the length in the Euclidean space of the image of the curve through your map U, okay? Now, this in local coordinates, if your map U is differentiable, you can actually write a system of partial differential equations with it. And the system of partial differential equation looks very innocent. So you take the partial derivative of u in the direction, say, xi, the partial derivative of u in the direction xj, you make the scalar product, and this should be the coefficient gij that you see in your matrix. So the question really is whether you can actually find a map which is solving this partial differential equation. And famously, John Nash actually proved and solved this, very classical problem by saying that there always exists a realization of your hypothetical world. Always. But in fact, there are even too many. There's many ways, actually, you could realize this world. So this is the first theorem he published. Actually, it has the name of Nash and Kuiper because Nash is doing the same for the mathematicians in the audience in a little higher codimension, and then he says that with a little work it can be done even in the actual statement of this theorem, and Kuiper writes down the details a little bit later. So this tells you that if you give me your hypothetical atlas, you can always not only find a realization of this, which is a real world, say, planet, but you can put it in a very small region of your space, which kind of sounds very odd, right? I mean, the length of the curves has to be the same as it's actually written in your atlas. So if the curve is 9 kilometers and you're putting it on a very small ball, it means this curve has actually kind of oscillate a lot inside to cover that much space. So it's going to be very difficult to drive along the road, right? I mean, because there are so many curves and with the car and so on. So actually, if you think about it, this is a pretty good realization of an hypothetical world, right? It's kind of boring because it's just completely flat, right? So you are an ant over here, you're just going straight, is the same as going straight in here. But of course, you could actually put your hypothetical world in this way, for instance, and the ant on top of it still would have to travel the same amount of time to go from here to here. Okay, if it goes over here, then it's falling, but never mind. Let's say there's no gravity. Now, it's okay, and I can actually make this very, 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 very thin in some direction, but many of you experience, often if you want to put it in a small place, like for instance your pocket, there's kind of this direction which seems stiff. It doesn't seem I can really do much about it without actually creating a fold, right? And it seems I need to create a fold to actually put it in my pocket. But this guy is telling you that that map actually is not creating a fold, right? I mean, creating a fold means you're going to have a discontinuity of the derivative over here. You're not going to have a nice tangent plane. But Nash is actually telling you that this shouldn't be something that you're actually doing, so you should be able to do it without actually crumpling the paper. So of course I could just fold it in this way and then put it in my pocket, okay? So it's a very counterintuitive statement. But by now mathematicians have learned that you shouldn't have too many opinionated like opinions on a theorem. It's a theorem. I mean, the guy proved it. So you might not like it, but it's a proof. But still, I mean, a very famous differential geometer of the time, Xin-Shen Chen, said like, yeah, this paper contains some surprising results. The embedded or immersed manifold is, of course, quite pathological. Which is a bit like saying, like, oh, you know, it's a lamentable scourge and so on. Like, okay, maybe it's also because Chern was Chinese, so less prone to drama than the French. But okay. Now, it's quite curious, though, because, you know, these two friends of mine, so Conti and Maggi in 2005, 50 years later, so these are two, I think it's actually not, with Francesco maybe less so, but Sergio is an applied mathematician. And they actually found that Nash's work can explain very interesting phenomena in elasticity theory, in which, you know, some people were actually proposing certain scaling laws for, like, you know, patterns or foldings and energies for certain things, and they're actually using this theorem of Nash, even though at the time, actually, Chern essentially thought that, okay, this is going to be kind of useless. I mean, an interesting curiosity, but kind of useless. Okay, so let me start with the third tale. So this is getting more and more into kind of analysis in mathematics, but, you know, bear with me a little bit, and then maybe it will get a bit relaxed towards the end. Anyway, I'm always going to tell jokes somewhat. So there's something which is called the theory of differential inclusions. So in the theory of differential inclusions, you're looking at problems of the following type. So I give you some set K, which is a set of possible matrices. And I'm kind of looking at maps which are going from Rn into Rk with the property that the derivative of u belongs to this set K. Okay? So this is what is called the differential inclusion. So differential because you're, like, you know, looking at the differential of the function, and inclusion because it's included in some set that you actually have decided. Okay, it looks extremely strange, but if you think about conformal maps, holomorphic maps, which are something which are actually kind of heavily studied, which kind of form some of the, you know, most wonderful pieces of mathematics in the 19th century, it's exactly a problem of this type, because a map is conformal if it doesn't change the angles. So this means that from R2 to R2 you have a map, and if you look at the derivative is actually a matrix which belongs to that particular set. So the Hilbert-Schmidt norm squared of the matrix is twice the modulus of the determinant. Okay? So, and then, you know, you're either holomorphic or anti-holomorphic locally if you solve this. So, I mean, it looks like a strange formulation, but there's actually a lot of maps which, you know, satisfy, like, you know, sub-problems like this. So differential inclusion are a very rich area of partial differential equations. So now let me look at the simplest situation, which is kind of boring. So I actually tell you that your set K consists of a finite number of matrices. And I'm trying to understand whether there is a map which is going from, say, some open set of R2 to R2, or, like, you know, from Rn to Rk, and whose differential is, like, you know, these few matrices that I told you should use. So here's a cartoon picture. So say that you have actually two matrices, and you insist from that, you know, your function has a derivative which is taking one value on one side of a line, and the derivative is taking another value on the other side of the line, right? But if I want the same map, this map has to be continuous along this line, right? So in here, the map will be kind of a linear function. On here, or an affine function. In here, it will be an affine function with a certain growth. But they have to agree on this line. And to agree on this line, it means that the slope of the function on this line, when you come from the left, is the same as the slope of the function when you come from the right. So you make a little computation, and what you actually discover is that if you take a vector v, which is directed along the line, the only way you're finding a map which is kind of continuous, which is taking the derivative on one side, which is a, and the derivative on the other side, which is a, is that v belongs to the kernel of the matrix b minus a, okay? It's a necessary condition if you think that your map is going to look like that. Okay, so the appropriate class of functions in which you actually look for these non-trivial maps are what are called Lipschitz. So Lipschitz means that when you look at the difference between the value of the function between 2 points, this is always controlled by a constant times the difference between the 2 points, okay, in absolute value. So these functions are differentiable at many, many points, and you can ask then whether it takes somehow these values, like, you know, if you find something non-trivial which takes this value. I mean, it looks like that the only way you could find something non-trivial, it's like, these maps are taking these constant values for the derivatives. There will be some region in which the derivative is B, some region in which the derivative is A. And if you're like having like 6 values, there will be a partition of your space into regions in which you take constantly each of the values, right? If you're sitting on an interface, even though the interface might be curved, there's going to be a story like this. So the only way you can actually find such a map is if the 2 values that you're taking here and here are compatible. And the only way to be compatible is to have this vector V in the kernel. And the only way to have that vector V in the kernel is for the kernel to be non-trivial. So if the difference between all the matrices, right, AI minus AJ, have determinant positive, which means that the kernel is equal to 0, you are you are naturally led or misled by the speaker of this talk to believe that there is no non-trivial map, right? So the map only takes one constant value. That kind of stands to reason. And now you got actually this theorem, which was proved in 2003. So there are 5 matrices, 5, in 2 by 2 matrices. And they have the following properties. So the determinant of any 2 of them, of the difference of any 2 of them is different from 0. So there's never going to be a map which takes one value on an open set, another value on the open set, and on the interface, the map is going to be continuous. But there's one map which is taking all 5 of these values in some crazy complicated way, which is not going to be a nice partition of your space. So the place where actually you're taking A1 is going to be kind of a crazy region, where you're taking A2 is going to be a crazy region, and where you're taking A5 is going to be a crazy region. So it's a remarkable theorem. Of course, it's a sort of monster, very counterintuitive. Of course, it's taking these 5 values, all of them, so the derivative of U is not constant. And it's a fantastic theorem because it's actually known in the literature that it is not possible with 2, it is not possible with 3, and it is not possible with 4. It does happen for the first time with 5. So it's a fantastic result. So let me go back actually to a portion of this story. So, what I kind of will try to maybe argue in this tale is that there's some kind of points in common between all these theorems, and then at a certain point also between something that I have done in my life as a mathematician. So first of all, Nash theorem. This is something that was dug by Gromov back in the 70s. So Nash theorem is actually not just some crazy occurrence of some crazy construction. So there's a whole family of problems to which you can actually apply ideas similar to what Nash does in the isometric embedding problem. And there's a theory behind this laid down by Gromov, which is called the H principle. So back in the 80s, 90s, and 2000, there were actually many tools which were developed by people in partial differential equations to prove theorem like the one of Kirchheim and Price. So these were people working in analysis, not in geometry. And Müller and Schwerak in 1999 actually discovered that essentially Gromov's H principle for the geometers and what people were doing in the theory of differential inclusions are closely related. In fact, you can kind of construct a type of H principle which kind of explains or applies to the problems of the people in partial differential equations. So now, in the early 2000s, actually, there was a general tenet that this H principle is anyway a mathematical curiosity. So, you can do it to certain problems in partial differential equations and in geometry, but you cannot do it, for instance, with partial differential equations which are coming from physics. In fact, Gromov gets the Budson Prize sometime in early 2000, and he gives this speech, and he says, the class of infinitesimal, okay, I don't know, I should maybe try a Russian accent here, but okay. But I'm not able to do that efficiently, so Michel will forgive me. So the class of infinitesimal laws subjugated by the homotopy principle is wide, but it does not include most partial differential equations expressing infinitesimal laws of physics, with a few exceptions in favor of this principle leading to unexpected solutions. In fact, and he's mentioning the works in differential inclusions, which some of them are originating from problems in nonlinear elasticity. in fact, the presence of the H principle would invalidate the very idea of a physical law, as it yields very limited global information affected by the infinitesimal data. So it's kind of saying like, your physics kind of sucks, actually, if the H principle applies to it. OK, so now let me actually get to the final tale. So this is Leonhard Euler, famous Swiss mathematician, countryman of mine, because I got the Swiss nationality too, thanks to my wife. So he actually derives more than 250 years ago the equations that describe the motion of ideal, frictionless, incompressible fluids. So you have a fluid which you cannot compress, which means you cannot actually, like, I don't know, for instance, water. You cannot actually squeeze a liter of water in half a liter. And which kind of moves frictionless. It means that you have layers of fluids which can kind of slide on top of the other in a way which is not creating any friction, so which is not like, wasting, for instance, any heat. That's, I mean, of course, both assumptions are actually idealization. So incompressible fluids are a little bit compressible. And perfect fluids which are frictionless don't exist, right? Well, you describe the equations. So he wrote down the equations. Actually, he wrote down more general equations. But so the unknowns that you have are a pressure, which is a scalar function, and the velocity, which is a vector function. It's very easy to tell you what the velocity is. So the velocity v is a function which is depending on a point in space and an instant of time. And it's telling you what is the speed of the particle of fluid which is passing at that particular time in that particular point. So it's a three-dimensional vector which is telling you the speed. The pressure is a bit more of a mystery, and I actually get asked a lot of questions about this. It's a Lagrange multiplier, really, of the incompressibility condition. Let me not dwell on it. So what I'm writing over here is the divergence of the tensor product of V with V itself. OK, so in coordinates, this means that I fix a coordinate, say, VI. This is what is going to happen for the ith equation over here. I take the product of VI with all the other components, Vj, and then I take the divergence of the corresponding vector field that I have created, so I take all derivatives in J. Okay? This is often written as the advective derivative of V along the flow. So it's often written by physicists in this kind of way, which, a typical mathematician finds it ugly because there's this V scalar nabla, so you're multiplying, something with another L, which is not really something you should multiply anyway. Well, it's an operator, whatever. But really, this is just the differential of V actually applied to the vector V. So sometimes I get, friends in geometry who are telling me, yeah, why is it written that way and not the usual way? Like we write it. It's like, I don't know. So it's written this way by the physicists. So what can I do? Probably Euler writes it this way, though. So maybe in the end, we have to blame a mathematician. Anyway, so what do they say, actually, this thing? So there's something which is called balance of mass. And this is really what the second equation tells you. So balance of mass tells you there's always the same amount of fluid inside of any portion omega. I mean, it's the far right paradise. So you're somebody at the boundary, so you have some cop actually there at the boundary. And if some immigrant is actually coming inside, you're actually kicking out some people from outside. Then you're actually kicking out some people from the inside to balance for that. So the total flux of people along the boundary has to be constant. Okay, really, I think the far right actually really wants it to be closed so that nobody is getting in and out. But it's a particular case anyway. And the conclusion that you get by knowing that the flux is constant is that the integral over the boundary of omega of v times nu is equal to 0. Now you integrate by parts and you use Gauss-Green theorem to actually say that therefore the divergence of v is equal to 0. Now there's something similar in which you actually balance the momentum. So you're using Newton's law, and the balance of momentum actually looks this way. So I'm not going to give you the derivation, but this is really what it does. It tells you that the total amount of, so this is the momentum because I'm assuming the mass is constantly, the density of the mass is constantly equal to 1. So you're taking actually the total, so the derivative of the total momentum is given by the flux of the momentum. I mean, there are some particles leaving with more money and some particles entering with less money, so you have a flux for the money, in this case for the momentum. But then there's also something which is a force which is acted by, at the boundary, and this is like directed orthogonally to the boundary and is multiplied by this scalar function, which is the pressure. So now here you understand the pressure essentially as a reaction of the fluid to the fact that particles are moving, and so if they're moving, they're trying actually to squeeze into some region, but you can't squeeze, so the pressure is reaction to that. Okay, enough jokes about actually politics, but I was about to say that maybe that's what we're seeing kind of right now in the current political climate. Now, you see actually that you don't need V and P to be functions which can be differentiated, right? I mean, to write down the balance of mass and to write down the balance of momentum. You just need to integrate. So if you have continuous distributions of velocities and pressure, you can actually understand being a solution of the incompressible Euler equation as for every fluid particle, or for every fluid region, you do have balance of mass and balance of momentum. Okay. These are actually what mathematicians, modern mathematicians in PDEs call weak solutions. So here's a theorem which was proved by myself and Laszlo Zekai-Hidi in 2012. So there are continuous distributions of velocities and pressure that solve actually these balance equations for all regions omega. So at all effect, they have the balance of mass and the balance of momentum from which actually Euler derived the equations. But these guys are compactly supported in space and time. And that is something very, very problematic. Because it means that there is this fluid, this hypothetical fluid, which of course is not a real fluid, which was at rest long ago. There was nobody acting on it, because there's no external force. Starts moving by itself, maybe during the night when you're not looking at it, and then stops at a certain point when you're not looking at it. And this is very, very problematic because I'm going to say it later. So first of all, maybe I'm going to tell you why it's problematic, because you might guess why. But so first of all, let me just say that this was discovered for unbounded solution by Vladimir Scheffer in 1993. And the second proof was given by Schnirelmann in 1998. Now, we first actually proved that this can happen for bounded solution, and then we did it for something for continuous solution. And this is actually a consequence of what I call the H principle. So there's an appropriate modification of this kind of theory, which was applied by Gromov to geometric equations, and which was applied by other people to kind of abstract partial differential equations, which actually applies to this. And this is an actual famous system of partial differential equations describing a very common situation, right? Perfect incompressible, like ideal incompressible fluids. So against actually what Gromov was saying in the Balzan Prize speech. Actually, in 2012, we suggested that this H principle could prove a long-standing claim in the theory of fully developed turbulence. So let me actually get to that. So, but maybe before I go to that, let me maybe just make a comment. So the Euler equation in which there's no friction has conservation of kinetic energy. So the only thing you're using is actually Newton law. And of course, if you start with the fluid at rest, the kinetic energy of the fluid is equal to 0. And later on, is also equal to 0, and then in the middle, actually, the kinetic energy goes up. Now, I got plenty of messages, sometimes emails from angry physicists who are telling me that I'm doing something which is just like, okay, it's a mathematical theorem, so I'm not trying to say that the actual real life works that way. Okay, so well, anyway, I get angry mails, yeah, but okay. So there was actually, surprisingly, the fact that this was not, so that this might happen, that something like that might happen, was actually suggested by a theoretical physicist who got the Nobel Prize in chemistry. So let me tell you how you get to that. So let me just add what is called the little viscosity. So now the fluid is not actually frictionless, but there's a little bit of viscosity. So you're multiplying by a small number times the Laplacian of the velocity field v. when the viscosity is positive, this is what you call the Navier-Stokes equations. And when the viscosity is equal to 0, this is what you call the incompressible Euler equation. Both of them incompressible. I mean, it's actually called incompressible Navier-Stokes. Now, if you have a differentiable function, solution of it, what you can actually do is you can use the basic rule of calculus and write down an identity for the kinetic energy density, right? So, I mean, if you see here, if you imagine that your density is constantly equal to 1, so here you have the modulus of v squared divided by 2, and you're taking the time derivative. So you're taking the time derivative of the kinetic energy density. And there's a flux term. So this is given by, a portion of this is given by the kinetic energy of, I mean, the balance of kinetic energy at the boundary of a sample by, fluid particles going out and entering in. Then there's like, this term over here. This is the work actually exerted by the pressure. And then there's what actually happens because of the dissipation, right? So you have a friction, and so you have something which is dissipated through the friction, right? Okay, you integrate in space, and what you find is that the total derivative of the kinetic energy is actually equal to this quantity over here. It's a negative number, right, multiplied by the integral of the derivative of v. So, of course, because you have the friction as you experience, right? I mean, if you don't pedal on the boat, sooner or later the boat is actually going to stop. So you need to actually keep feeding some energy to the system to actually keep moving. Otherwise, the thing would kind of try to actually go at rest with the friction. Now, you need some assumption for the mathematicians, right? So I'm doing this on the whole space. So either the fluid is at rest somewhat at spatial infinity, or otherwise, solve your equations on the periodic torus, which, we don't live on the periodic torus, possibly. Who knows? I mean, maybe the relativists actually are going to tell us that maybe yes. I don't know. Anyway, so he does it on the periodic torus, on Saturn. So the monster solutions, like the one I told you, violate this law, right? I mean, because nu is equal to 0, and so the total kinetic energy should be constant. Of course, I missed a factor 1/2 over here, right? Because I'm integrating that. Okay, forgive me. And as I told you, the solution of the Euler equations, which I constructed together with Laszlo, are not actually satisfying too, because the derivative of modulus of v squared should be equal to 0. So if it started being equal to 0, it's constantly equal to 0. And then v is constantly equal to 0, because its integral vanishes. So now, assume the viscosity is actually positive but small, right? So you have this balance law. And if you open a book in physics and you happen to actually learn about this Kolmogorov's theory of fully developed turbulence, one tenet of the theory is that, well, actually, most solutions have this Q of t, which is independent of epsilon, but has a certain law with the size of E of t, with this beta, which, it's independent of epsilon. So there should be a dissipation which actually survives even if you let epsilon go to 0. So there's some assumption that you actually have to put. So at this point, you might actually, as a mathematician, think like, OK, let me switch off the friction. Let me actually let it go to 0. So I'm solving Navier-Stokes equation with a number nu, which is smaller and smaller. So I'm getting closer and closer to a solution of the Euler equation. But these guys are actually telling me that the right-hand side keeps being constant. So in the limit, my solution of the Euler equation cannot have that the energy is conserved, because that guy is actually going to survive and be a number, I don't know, -1. So the final solution cannot be a solution, a classical solution of the Euler equation. It has to have constant energy, energy which is decreasing. Of course, my fellow in physics would say but it's decreasing, right? It's not increasing, so there's no problem with the fact that I constructed a solution which at a certain point has energy which is positive and then goes down and goes to 0. What is really surprising is that your solution had energy which was 0 and then got up. But the Euler equations are perfectly time reversible. So whenever you actually find a solution which for you is legal and has the energy which is going down, I apply a transformation and find the same solution with a couple of changes of signs changed. And actually this solution is having the energy which increases. Now, of course, I've changed the arrow of time. But if you don't tell me what is the arrow of time, and you're just a bloody mathematician, the solutions with the energy which is increasing are there staring at you, as soon as you have something actually with solutions which have energy decreasing. So it's really actually this is what you're expecting, somehow that you have non-trivial sequence of classical solutions of Navier-Stokes, which, blah, 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 they converge to Euler. I can't prove this. Nobody can prove this with reasonable assumptions. So as far as I'm, it's like a stubborn mathematician, I would say, like from the equations, which is where I actually would like to see this consequence of Kolmogorov's theory, I cannot make any prediction. But Lars von Sager, back in 1949, actually, he rewrote Kolmogorov's theory independently, and he said, like, hey, well, I could put epsilon equal to 0, and everything that you're doing is OK, and then you have ideal turbulence. And in this ideal turbulence, you have solutions of the Euler equations which do not preserve the kinetic energy. He actually went a little bit further. So he advanced what we call a conjecture in mathematics, so something like that you hypothesize. Although if you actually read the paper, he's never using the word conjecture. He's just telling you this is what is going to happen. That happens to me very often when I talk actually to my friends in physics. They just tell me, OK, this is reality. And then I prove something, and they tell me, like, but reality is not that. OK. So you assume you have a periodic solution of the Euler equation. And now you remember we studied functions which had, like, bounds. I call them Lipschitz, in which the difference between the values of the function at some points is controlled by constant times the distance between the points. But now Hölder functions have actually the property that this inequality is made with an exponent alpha which is not exactly equal to 1. And what the conjecture is that if this, if you're looking at solutions which are kind of regular enough, so they have this exponent alpha which is above 1/3, then the total kinetic energy is conserved. But as soon as you actually try to get rougher solutions, there are some of them for which the kinetic energy is not constant. So this alpha equal 1/3, which you can try to get with some heuristic considerations out of back of the envelope computations like dimensional analysis, is actually something which is specifically linked to the theory of Kolmogorov. So it's not like a casual exponent over there. It should be the threshold for the behavior between these two types of solutions. And often my friends in mathematics, when we actually say that a physicist conjectured something, what we really did, we took a paper in physics and we kind of extrapolated something, and then we wrote it in mathematics, and then actually we called that a conjecture of that physicist. But typically in this translation, we did something nasty. It's remarkable because if you read on Sager 1949 paper, he gives a precise definition of everything over there, including what it means to be a weak solution of the Euler equations, because he says, well, the function is not differentiable, so I have to tell you what it is to be a solution. And he does that with Fourier series. It's remarkable. So he gives a very rigorous definition by expansion in Fourier series. So now in 1993, actually, the first part of the conjecture was proved by Eying, almost proved by Eying, a student of von Sager, and completely proved by Konstantin A. and Titi, exactly in the way von Sager stated. And now, concerning part B, I told you, there's a Schaeffer's example, which is the first rigorous instance of something which does not conserve the energy. In 2012, we actually suggested that our theorem might be thought as a starting point of a program to attack this part B of the conjecture. And it was proved, actually, by Phil Isaac in 2017 after, a few progress by ourselves and other people, some students and collaborators, but then finally Phil was actually able to make this conjecture a theorem, which is a fantastic result. In fact, let me make a little bit of advertisement for two very young PhD students of mine that in 2023 actually found a much simpler proof of this theorem. Okay, so let me just tell you a little bit how you can construct these monsters. So you remember Ideally, we would like to actually construct these solutions of Euler as limits of solutions of Navier-Stokes, but we're not able to do that. But we are able to construct them as limits of solutions of a more complicated system in which instead of having like, the viscosity, the actual viscosity, we have the divergence of some tensor on the right-hand side, which is called Reynolds stress. It's actually something which is widely studied in the theory of turbulence. So the tensor RQ, in a sense, measures your distance to a true solution of Euler and converges to 0 in the limit. So the key idea is that you're actually going to produce VQ, PQ, so, sorry, not VQ, PQ, but, VP. So, okay, so the idea is that actually your solution V and P are produced as limits as Q goes to infinity of this VQ, PQ, but the key idea is that at each iteration, at each step of the iteration, you're actually constructing a new solution for which this tensor is considerably smaller than as it was previously. So you're actually trying to correct your approximate solution to be a better approximate solution along the sequence. And the building blocks are actually highly oscillations. I mean, they're very oscillatory functions, which are stationary solutions of Euler, combined in a certain particular way. And these blocks are very highly periodized. You make them much more periodic compared to, say, what was the periodicity maybe at the previous step. And you transport it along the flow of VQ. So I'm actually going to give you a very small toy example. So bear with me 5 minutes. This is going to be the kind of most mathematical part and maybe the least fun. So say that instead of trying to solve the Euler equation, you're trying to solve a PDE problem, which is much easier. So you're trying to actually produce maps which have modulus of the gradient which is equal to 1. So this is called the iconal equation. And maybe you want to put some boundary conditions so that you're not looking at a linear function. So the plan is to set up an iteration mechanism. And in this iteration mechanism, you have some approximate solution. So some phi 0 that you start with, whose length of the gradient is a little bit below 1. And now you want to produce a phi 1, which still has the modulus of the gradient, which is less than 1, but which is much closer to 1. And then you want to produce phi 2, phi 3, and so on, and eventually take the limit of this map. So this is what you want to do. So you want the modulus of the gradient of phi k to always be below 1, but the distance to 1, which I can compute with this integral, should kind of shrink by a factor beta, which is less than 1 and is independent of k. So each time that I actually progress on my step, that total integral, which is measuring how far actually you are from being a solution, is going down, is converging exponentially fast to 0. Okay, so here is a way actually I'm going to do it. So you start with your, I forget about everything that happened in the past. So you give me your function phi k, and I'm going to produce my function phi k plus 1, which is a much closer to be a solution. So your phi k is actually nice. It's a smooth function. So locally, if I look at some region, the gradient is almost constant. And when the gradient is almost constant, I see a very nice constant slope. So here I'm taking some small region, and I'm magnifying it to a very big one, just because so I can draw pictures. So what do I see actually on that region? So on that region, I see a slope. I mean, I don't know. I see a slope which is maybe going this way. So I put myself orthogonal to the line of maximal slope, so that I'm on the constant, say, values of the function, right? So I put myself over here. I look at cross-section. And now I know that this slope is less than 1. So I would like actually to make it closer to 1. And what do? I start oscillating back and forth between two slopes which are exactly equal to 1. But I don't want to do something like this, a zigzag which is kinky. So I smooth it a little bit. And if I smooth it a little bit now, you see why I'm taking an integral. So most of the times, I actually have a slope which is very, very close to 1. And then I have a small region in which I have to go around and go back. OK, I can do this. Now I can do this, but you see, one problem is that over here, I might be going on a slope in this way. And over here, I might actually going on a slope on that way. And over here, I want to add an oscillation like this. Whereas over here, I want to add an oscillation like that. And obviously, they are incompatible. I cannot do that. So I can, though, multiply by a cutoff function, c of x, right? And the cutoff function actually makes it sure that when I get close to the boundary of this sample, so the cutoff function will be equal to 0 over here and will be equal to 1 a little bit in the interior, say over here. But the cutoff function makes sure that my perturbation remains local, and it's not going actually to disturb me far away. Okay? So you have a formula for this perturbation, right? So this perturbation over here takes this formula over here. The reason why, see, lambda is the periodization. The reason why you put 1 over lambda is because when you compute the gradient, the lambda gets out and kind of cancels this. And you see kind of really that, you know, the perturbation in the terms of the gradient is of a certain size. So it's not surprising, right? I mean, if I make actually my oscillation faster and faster, the curve will be like tiny, tiny, tiny waves, like, you know, oscillating on top of the guy. So, okay, this is my formula, and this is the wonderful miracle that happens. When I compute the gradient, I get the original gradient of phi. Then I get the derivative, which is eating p, because I'm using Leibniz rule. And this function is mostly 1 in the region where I actually want to improve. And if this function is mostly 1, in that region, I'm really exactly the sinusoid that I wanted to add. But then there's an error. There is an error because maybe I differentiate the cutoff function. But this error is very, very small if my lambda is huge. So what will I do? The improvement pushes the slope towards 1. The error can be made small if we make lambda very large. And you know, you take care actually that by doing this operation, you stay below with the gradient, right? Below 1. Because if the slope was bigger than 1, I couldn't bring it down to 1 by adding a perturbation, which is an oscillation, because I would actually have to go faster somewhere. So now what do I do? Well, you know, I cover a good chunk of my omega, maybe, I don't know, 1/10 of it, with tiny, tiny, tiny balls, and in each of them I put my tiny, tiny, tiny oscillation, and this is how I actually produced from phi k plus 1. Now, the upshot is that all these crazy constructions, so, you know, this one that I told you for the Euler equation, but even when you go back the Nash construction, and even when you go back the Weierstrass construction, it's actually following all of this pattern, that you're piling up crazy waves on top of crazy waves, with a lot of spacing between them. So here's Weierstrass, actually. The Weierstrass function has a very special form. It has this form over here. So it's a Fourier series with a lot of tiny oscillations on top of the next one, right? So it's a lacunar Fourier series in which you're skipping a lot of frequencies. And, well, you know, it's a fun exercise to actually prove that this function is continuous if you choose A and B correctly, but it cannot be actually differentiable anywhere because the difference quotient of this function actually is going to infinity in absolute values everywhere, okay? It's a fun exercise. Thank you.
Thank you very much. Is there any question for Camillo?
Okay, I might be slightly biased in my question, but your discussion on Euler equation means that to catch physical behavior, it's better to go to stochastic case?
Ultimately, that's what you would like to do, right? I mean, kind of Kolmogorov tells you you should see this anomalous dissipation most of the time, which, of course, you would like actually to understand in some statistical way. Nonetheless, I'm kind of a curious guy, so I do like probability. But when I go to the casino, I just want to win that singular time that I go there. So in particular, okay, even if you tell me that, you know, my sequence of solutions, Navier-Stokes, should exist because actually I should find them with probability 1. My problem is that I can't find a single sequence which is doing what I want, which is what I would like to prove as a mathematician doing PDEs. Now, if I had, of course, a way of doing this statistically, I would be even, much more happy. So in all I told you, actually, there is something which is not exactly stochastic, but it kind of flavor like that, which means that, for instance, there's a way you can understand that, you see, I generated, for instance, in the toy example, these things with, the phi k plus 1, and so on. I gave you a precise recipe, but if I were doing those things kind of at random and adding, like, some ways in a sort of more messy and chaotic way, I would still actually kind of get, in the end, at the same kind of behavior. So there's definitely some probability or some, like, statistics lurking there, which fortunately, I cannot quite pin down. But yeah, so possibly.
One curiosity I have is, when you're finding solutions to the Euler equation which do not conserve the energy,
yes,
this violation of the conservation law comes from the definition, the weird definition of solution for low regularity, I would say.
Right. Weird definition of solution means, of course, that it's just the low regularity, not the weird definition of solution. Because if you were as regular as being able to take one derivative, the definition I gave you with kind of the fluid elements is actually equivalent to the equation. In fact, in the books in physics, in the books in continuum physics, they derive the Euler equations the way I told you. So they kind of they go and they tell you, oh, there's a continuum, and the continuum has to satisfy the following balance law. Balance of mass and balance of momentum. Okay, balance of mass is what I wrote down. So you integrate by parts, it's divergence, the integral over omega of divergence of V equal to 0. And because divergence of V is continuous, for instance, if you see one, if the integral is vanishing over all domains, then divergence of V is equal to 0. That's the literal way, actually, classical books in continuum mechanics derive the equations of continuum physics. So from that point of view, it's not a weird definition at all. Of course, the fact that you're not regular enough then makes that thing kind of possibly happening. But it's not. You see, okay. So it's not something that, is unknown in physics. In the theory of shock waves, this is kind of very well known. If you have, for instance, compressible fluid dynamics might create singularities. And on those singularities, you might have a shock wave. Okay, on a shock wave, certain conservation laws are not valid anymore. And then, there are certain inequalities, but then the conservation laws are not valid anymore. Some of them are, but some others are not. So what actually makes this very, very, very surprising is that if you try to make that happen for Euler on a classical singularity, for instance, on the typical kind of singularity, which is jumping between two states, you will not be able to dissipate the energy. So the dissipation of the energy is not a simple singularity mechanism, but it's a very complicated singularity mechanism because your solution has to be singular somewhat everywhere. But I would argue that it's not, that singular solutions aren't kind of satisfying certain additional balance laws. It's actually something that we knew even very long ago. And whether that is weird or not, it depends on, what kind of behavior you're trying to capture, essentially.